Hello. Okay. All right. Okay, everyone. Welcome to our week 3. So this week we'll talk about the fundamental of machine learning. Okay. So again, before I start this today's classes, I want to clarify the difference about the fundamental of AI in applied AI discourse and the fundamental of AI in other courses. So because this is only the applied AI, so we don't touch any about the math stuff, for example, some very detailed serial parts. Okay, so this part of fundamental of ML is mainly to inform you about the machine learning's pipelines. So it's more particularly when you utilize the machine learning model, which process you need to take step by step. Okay, so during this process, what kind of the stuff you need to take care of when you utilize this machine learning algorithm. All right, so let's begin. So today we will talk about firstly the ML models. So that's what I said. We'll briefly talk about some very general classification about the AI algorithms. Categories, okay, and then I'll briefly talk about with some cases. So even though you don't know what kind of which algorithm need to be choose to solve your problems, but at least you know from which category you need to choose to solve your problem. Okay, and then we will have a first look at ML models. To give you an example about how to utilize this ML model to solve the problems in your real world. And during this, during your solutions, so when you utilize these models, what kind of things you need to answer before you utilize this model. Okay, so that's the first two things. And the third thing is, third and fourth is remaining about when, after you have already selected about the algorithm, the models, how to make it perform better, okay? And to evaluate whether this performance is met your satisfactions or not. If not, what to do. All right, so this is the briefly about today's structure. Of course, today, it just gives you a kind of like a warmed up, okay? For the following weeks, we'll talk about more detail of the specific algorithms and when you utilize it, how to take care of their the model's pipelines, what kind of things you need to mention during your model's constructions. And when you develop these models, how to consider about their generalization things, optimization things, and finally evaluation stuff, okay? But this is kind of like warm up, all right? So first, all right, I think I need to put the learning objective before that. Of course, the learning objective, you will need to distinguish between the different learning paradigms in ML and some key difference between the parameters and hyperparameters. And have a first look at what's the training and inference with a neural network, and final understanding tension between the generalization and optimization. Okay. Which is a fundamental issue of the ML. And of course, you need to name and explain the factors that lead to overfitting. Okay, we talk about the generalization and optimization's relationship with the overfitting stuff. All right, and finally, you need to understand about the evaluation metrics. Okay, so I just want to highlight here. Okay, when you talk about an AI project, except for in the first class, we do some practice about, okay, what's your target, right? And what's your training data, how to identify the high quality training data. Except for that, another important thing is the first thing is what algorithm you need to choose, okay? And the last thing is to identify your evaluation metrics, okay? So, the other thing I want to record from the week 1 machine learning. So machine learning again is searching for the useful representations and rules over some input data using the guidance from a feedback signal. Okay, so this is a very brief idea when we talk about in our week 1. However, when we dig inside or dig in depth about machine learning, you need to utilize some paraphrase to replace those words. For example, what's the useful representations? That's what we talk about. What features? Okay. So the features in the traditional machine learning. What about in AI? For example, in the image, number of channels. Okay, so that's the useful representations. Remember, number of channels, if it is the RGB, that's the switch channel. If it's the RGBA, A actually as the alphabet for the transparent parent. Okay, transparency. Okay, so that's the third channel. And how about the grayscale image? Grayscale image, that's one channel. Okay, so all these you actually are all included in the representations. Okay, but with different kind of task as an AI expertise, you should understand. Okay, what's the useful representations means. Okay, and rules over some input data. So how to find out these rules? Just recall about what we talked about in week 2, right? So in week 2, we understand about how to do some data processing, some idea, okay, so to do the visualization. So I show you about for example, you visualize it, you have a glance look about what's the distribution of this data. Okay, so that's, you can understand about rules. And what else you can find the rules? The rules normally will guide us to choose what kind of machine learning algorithm we want to select. Okay, so decision trees is normally different depending on different conditions. Okay, in multiple conditions, you need to make decisions one by one, and that's the way you better to choose decision trees, random forest. Okay, if it's like the decisions with the round table, a distribution of about a round, then that could be SVM. Okay, if it's quite separate design, you probably just need to utilize the linear algebras that can solve the question. That's all the traditional rules. Okay, so what the rules over some input data? What if it's in AI? For example, the text rules, time series. Okay. Audio time series data. Okay, so when I talk about the text, when it's a time series, that's the when you predict the next word, etc. So that's the time series. So with time series, in our later classes, you will understand that if it's a time series based data, the rules that you need to find behind this time series based, then you need to choose the RNN or LSTM. Okay, so that will allow you to learn what's after, what's before. Okay, learn from context. All right. So if it's the image, then actually you need to learn from the pixel to understand the whole stuff. Then for this kind of data, the rules need to be, it's not the, it's still the context, but it's from small to large, then it's the CNN, fully connected neural network. Okay, so that's all you need to learn. The rules under the different kind of input data will help you or guide you to choose what kind of algorithms you need to train the model. Okay, so and after that, okay, you understand about so when you are expertise, you learned okay for specific tasks what you can represent the useful representation. You will understand what is the rules over some input data and what's the guidance from the feedback signal. Feedback signal is when we talk about related to the evaluation matrix. Okay, so normally we talk about it as a loss function. The loss function actually means the classification error. Okay, classification error we told you when we run this learn these rules, whether their learning direction is correct or not. If it's not correct, then maybe I will need to use the guidance. In AI, we normally talk about it as the gradient. Okay, gradient will guide you to learn the things from the correct direction. Okay, so the feedback signal, when we normally talk about, is the loss function. Okay, and loss function is based on the prediction and the true results. Okay, so that's after the whole courses, you need to represent all these like large concepts into more specific one. That means you are able to solve a real world questions. Okay, so again, while we were learning the rules around representation from the data, you firstly need to understand about the input data points. So that's what we say the training data. The second is expected output. That's what we call the label. Okay, and an error measure. That's what we call the measure. Evaluation matrix. Okay, so I have already talked about that previously. As you can see that here, give you a heads up. Here is, as you can see, the error message. It's current rules, current output, and what we expected output. Expected output normally we will say is the ground truth or the label. And the current output is what we said, it is the prediction output. Okay, so when we compare the prediction output with the true output or with the ground truth, and we have the error message, so this error message will guide the current rules, that's the algorithms or models training step, to predict the more accurate prediction results. And by those comparisons, by adjustments, when the error message is the lowest one, then we can obtain our satisfied model. Okay, so that's the satisfied rules after the adjustment. All right, so that's the brief idea about the learning paradigms we have already talked about in the week 1. And then we want to talk about, that's a very general learning paradigms. However, you can, for this very large concept of the AI, you can actually divide it into 4. All the algorithms are classified into these 4, okay, including the supervised learning, including the unsupervised learning, reinforcement learning, self-supervised learning. Okay, so as I told you, after you find out the rules, you can actually at least choose whether it's supervised learning or unsupervised learning, or you need to use reinforced learning or self-supervised learning. Okay, so after you find all these, the rest of the step is you probably just choose a set of the algorithm from those categories and use your training data to feeding different kind of like the AI algorithms and test which algorithm is suits best. Okay, but the first thing is you need to understand which learning paradigms suits your problem. Okay, so let's talk about the first one, supervised learning. Okay, supervised learning, that it's what we normally utilize. Okay, it's a machine learning task to learn a function that maps an input to an output based on the example input-output pairs. What it means? It means the model is based on the example input-output pairs. That means we do have the input, which means features, okay, and then we do have the corresponding output. That means the label. Okay, that's our input and output. And this is the most common learning paradigm in the real world, and it will require a label for each example. So normally we will call the input as X, output we call Y. F will call the function that we try to learn the rules that X map to Y. Okay, so this is so it's X map to Y. Okay, so this is the function's algorithm, F. All right, so expected output will often interchangeably called label or targets. Okay, so these will be label or target, that's Y. Okay, so the task normally includes binary classification. So binary classification, that means this Y only includes two labels, that is 0 and 1. Okay, normally we will classify it as 0 and 1. Of course, you can replace it with 1 or -1 or etc., but they only have two categories. Okay. The second is multi-class classification. So multi-class classification, the Y is belong to a set of the labels. Okay, why we do this classification? Because with different classification, the evaluation matrix will be different. Okay, so that's why we classify it as this. Okay, the last thing is regression. Okay, regression is particularly for the numerical stuff. Okay, so especially this, that it means the Y here, it should be the numerical. It cannot be cat, dog, bird. Okay, it must be numeric. For example, 0.1, 0.2. So this is their output. Okay, so that's what we say, the predicted number of units sold the next quanta. So that's an example. But I want to take a very brief idea about how to identify whether we need to use supervised learning or not. Simple one is when you can collect the label for your training data. Okay, if that's the case, definitely the supervised learning is your first choice. So for example, there was a case we always talk about in our previous classes, the student performance prediction systems, right? Remember that the training data that we said we can collect it from is what? Grade, your log activity in Canvas, attendance rate, and what else? Anyway, okay, so if when we have this kind of, all we talked about previously is the features, okay? And then what's the label? Can we obtain the label? How we identify the student's performance? Any idea? If this is the AI project, what's the student's performance you can utilize? An example? Yeah.
Grade.
The grade, yes. So it's the numeric, or yeah, it can be numeric, right? However, here, okay, so if you consider the student's performance is great, okay, that's the numeric, and then you need to choose the task regression. Okay. So any other kind of like the format that we can utilize to represent the student's performance? Any other idea? HDDC. that kind of like range, right? If we put HDBC, then what's the task we follow? Multi-class classification. Okay. So what if I want it just a binary classification? What we can label this performance? Yes, fail past. Okay, so that's the binary classification. Okay, so it all depends on your labels. Okay, labels type or the number of classification. So that's how when you have your data, you will understand what kind of like a learning algorithm you need to choose. Okay. Now, how about the unsupervised learning? So firstly, the unsupervised learning is what we say that only the task to learn the patterns. Okay. They don't. The previous one is what? Is learn the patterns that includes the mapping, right? Includes the mapping. But the unsupervised learning is I want to learn the patterns within this X only. I don't want to find these patterns of relationship with Y. There's no Y here, and that's the unsupervised learning. Okay, so that's what we say, the machine learning task of learning patterns in the input, even though no explicit feedback is supplied. So that means we don't have label available. And normally we will say the unsupervised learning is the clustering problem. Okay, clustering means gathering the data with the similar patterns or similar attributes. So here, normally we will say attributes is also we mention as the features. All right, so there were some models, what we call is the latent variable model. So this model is aiming to finding the unobserved variables that explain the most of the variance. What it actually means. So normally when we do some visualization, do you remember when we do the visualization? The first thing what we need to do when we visualize this set of data, what's the first thing we need to identify? X, Y, Z, right? If you don't identify the X, Y, Z, how could you visualize it in the space or in the 2D space, okay, or in the 3D space, okay? So with this 2D space or 3D space, the pattern that we observed is actually the pattern between those 2D or 3D. You got what I mean? So perhaps it's for example, if it's a 3D, then this shape is not just in XY phase, or it's not just in the YZ, it's not in the XZ, it's actually in the intern space, right? So that's the space, or that's the feature you haven't yet identified, okay? So remember the last class that we say how to transform the XY axis. So in the XY, right? I will show you the previously. Okay. So for example, in XY, that we find the original the data's distribution is look like this and this. No, and this. Okay. So I find some patterns that actually can better reflect this data. Is what? It's in this direction. Okay, it's in this direction. Okay, so the second axis is actually another feature that I find. Okay, another feature or another space that I find can actually really reflect the data that I collected. So this is what we say another attribute, or we can say this attribute is what is the patterns, unobserved variables that we found. So here is we normally say the variables is our X. Okay, it's our X. So this is the unsupervised learning. I think I actually can see lots of confused face here. So I want to use like some practical example to talk about it. Okay, so for example, we try to create a clustering model to segment the customers based on their purchasing behavior, okay, frequency, and the spending patterns. So what kind of data we can collect it if you want to check out the customer's feedback about one specific item, whether customer like it or not. Any data that we can collect it? Any idea?
Star rating.
Yeah, star rating. Yeah, right. And what else?
Reviews.
Yeah, reviews. What else? Star rating, reviews.
Sales numbers.
Sales numbers. Yes, definitely. But the sales numbers, they have some problems. Is you need to identify the sales number is for this particular product or it's the sales number from specific customer. Right. So because your unit is one customer, okay. If you identify that the whole sales number is the total amount of this product sales, then it could not reflect individual users or individual customers' feedback. Okay, so then we can currently obtain three things. Yeah. What else?
Maybe the frequency of other product.
Yes, frequency. Frequency. Okay. I think that's it. Okay, I think that's it. All right. So with all those, perhaps we can have more. For example, for this particular customer, you can understand his or her own spending patterns, shopping patterns. Okay, that also related, right? So if you singly look at the starting rate and the feedback, it normally say, okay, this is a very good product. I love it. The shape is so good. Okay, and I give them 5 stars. Okay. However, when you check on, so this is the one pattern. Okay. However, when you check on it's the whole stuff, you might consider, okay, this customer loves this product the most because it's 5 star, because it's very positive feedback. However, when you check on the other kind of like variables, for example, the customer's spending habits. Okay, so the customer spending habits, he or she buy lots of this stuff frequently, and he actually just buy this stuff once, and he or she rebuy or repurchase the other similar product multiple times. And this customer's shopping habits is always leave the positive feedback, because the positive feedback can give him or her about some, there was some prompts, okay, or just small amounts of the the win back because of the positive feedback. Okay, so these kind of things, when we normally would not consider, however, when you gather all those informations with regards of the information, you might detect it, okay, this product maybe is not the user's preference. Okay, it might lack of something. So by considering lots of information, you might find some unobserved variables, for example, the user's habits that actually indicate this is not the product that she performed the best. Okay, so that's what we say, finding the unobserved variables. But by finding the unobserved variables, the key term is actually I have enough feature. And it's just enough feature that together will reflect another feature that we haven't considered to collect. So for example, the students provided haven't considered to collect these customers' shopping habits, right? But with enough data for this, from this customer, from these products, you might be observed these kind of things. Okay, that's what we say to unsupervised learning. All right, what's the reinforced learning? Reinforced learning is what we normally in the game. Okay, so win and when they have like scores, okay, so reinforced learning is the machine learning from a series of, it's machine learning from a series reinforced, that's rewards and or punishments, okay? So it's training an intelligent agent which actions to take in some environments in order to maximize its rewards. So applications, for example, the games, for example, Go, Dota 2, and robots. Okay, so I want to give a very brief description about an AI project here. Is, for example, an AI agent that optimizes the traffic light timing at the intersections to reduce the simulated traffic environment and receiving the rewards based on the metrics like reduced waiting time. Okay, and try to minimize the vehicle's queue length and improve the throughput. Okay, so we think here what kind of data we can collect it for this project. Reinforced learning, what kind of project? What kind of data we need to collect? Again, I try to reduce the congestion and improve the traffic flow. More specifically, is try to give rewards based on the metrics like reduce the waiting time, okay, and minimize the vehicle queue length and improve the throughput output. Okay, for this kind of like ad project, what kind of features or data you can collect it? Any data you think is related to this award. Okay, remember for applied AI, the most important thing, as long as you find qualified data, the rest of thing it can be solved fluid. So what's the data you can collect for this AI project? Any idea? According to the metrics, reduce the queue time, minimize the
Well, I'm not sure if it's correct, but for reinforcement learning, usually we have like something called a fitness function, which is just like a numerical value representation of how good the algorithm is doing. So we take into account the amount of like waiting time and the amount of cars, and then we give it different weights depending on how important those things are to us.
Yes.
And then the AI or the reinforcement learning algorithm will just try to get the fitness function depending on how the weights are to get as big as possible, get as high a score as possible.
Yes.
So we would need like some sort of device that can count cars or like a counting system or something that can figure out where the cars are, how many cars there are, and then get put into the fitness function, and that then tells the algorithm if it's doing a good job or not.
Yeah, that's great. You almost talk about a whole AI project. So you just need to summarize like what kind of data you need to collect as I just summarized from your previous description.
Which is number of
cars, waiting time,
amount of time it waits.
Amount of time it waits.
That's basically everything.
Amount of time it waits, and I think you need to consider about the amount of the car, right? Because the length of queues.
Yeah, number of cars.
Number of cars. Yes. And I think there was another thing need to be considered is about the timing, the period of the day, the period of the time. It's because when of course you need to you have clear idea about the features, right? But what's the high quality training data that can allows your feature will obtain the most important information. The information is not biased. So that means we need to collect all those data in the traffic congestion time. For example, the morning between 7 to 8 or 7 to 9 a.m. And after office hours, for example, I don't know, maybe 4 to 6 or 4 to 7. Yeah. So and there was some empty some idle time. For example, the 1 to 2 a.m. right? So all those need to be considered, and also the waiting time. If the waiting time is not just the amount of car, but also the amount, also about the pedestrians. Okay, so if that's the case, you need to also consider about the pedestrians' waiting time as well. All right, so that's what we mentioned. Yes, if you don't understand about what's the high quality data, you can count it. The first thing is just what you did. Okay, you can consider about what's the features you wanted, and according to that features, you find out what's the high quality data you want. All right, so that's the reinforced learning and self-supervised learning. Well, again, the self-supervised learning is actually it's very similar to the unsupervised learning, but they have some difference. But self-supervised learning is more like filling in the blank. Okay, the self-supervised learning, it means actually the training data, they don't have the label, so does not require the label. However, based on the features, they can learn the features themselves. It's a kind of label. It's kind of label. Okay, so for example, the next word prediction. Okay, so next word prediction, normally the training data is what? It's a full sentence. Okay, it's a set of full sentence documentation. So that's the training set. And the input is what? If we just consider self-supervised learning as the supervised learning, the input is the first part of the sentence, first part of the words in this sentence. And the label is what? Label is the word next to the previous word. Okay. And in our training data, we didn't give them the label. However, in one sentence, they include both their features and the label. Okay, we just cannot, sometimes the label will be the features, and sometimes the label is the label. Okay. So that's what we say. This is the self-supervised learning. So normally we will have the auto-regressive model, so predict the next element of a sequence given the previous ones. So that's what we say next word in text. And another one is the mask auto-encoder. So this is what we normally say the transformer. Okay. So the transformer it's not just to predict one word in a sentence from another word, but it also includes if I give you an image. So you learn all the image's pixels value. However, this part is mixed and I want you to fill in. Okay, so that's also the self-supervised learning because you learn the whole context of this image from the rest of the pixels, right? And based on the rest of pixels, for example, its neighbors, it can simulate what its neighbors behave and fill in these pixels values. Okay, so that's what we say the self-supervised learning. All right, another kind of thing is constructive learning. This one is normally between the augmented views of the different examples. I do remember in the first 2 weeks, the students asked, some students, not just one, asked me when we have very limited data, what to do. Okay, there's lots of ways we can do. First, you can utilize open source data. Okay, the open source data can be found in the for example, the Hugging Face can be found in the GitHub, can be found in some specific institution. Okay, they will publish this kind of like open source data. Okay, except for that, you can generate your own data. That's what we call data segmentation. No, not segmentation. Sorry, synthetic data. Okay, so synthetic data, this is one way that we create synthetic data, is the augmented views. So give you an example, if we have very limited image of the Aboriginal people, okay, so what we normally do? No, don't take the Aboriginal people as an example. It's very sensitive. Okay, let's talk about for example, the plant. Okay, if we have very limited image about the plant, and we want to called the plant, the different kind of plant classification, what we normally do. For a specific kind of a plant, we have very limited, just 1 or 2. And for other kind of the plant, we have like 100 samples for each. So what we normally do for this plant, we have a few ways to do. Okay, we can rotate the picture. So if it's flying like this, and then we rotate it, it's like flying as this. Okay, that's another image. And also it's countable. Okay, what else? Change the color. Okay, what else? Change the size. Okay, what else? Change the background. Okay. Okay, so all these are what we say is including as augmented. So augmented data is the most thing that is more close to the real world data. Okay, it just changed some noises, right? So that's the augmented data. Of course, we have other kinds of like segmented data. Okay, this is just back to the previous one. If you want to increase the limit of the data, except for the open source semantics and what else? Actually, you can find similar data, data from a similar area but different distribution, and then somehow you can use the transformer to transform the knowledge back to your desired area. Okay, that's the most advanced thing that you will need to learn at the very later of our courses. Okay, we won't talk about it here. All right, so the constructive learning is you don't need to give the label, although you don't need to give this is augmented views and this is the original image. You don't need to, but you just need the constructive learning to learn, okay, because you just have these 2 labels and just learn the difference between them. And that's actually you have assume the label within that. Okay, so that's another self-supervised learning. All right, so that's all the learning paradigms that includes almost all the real-world problems. Okay, so when you get obtained a project, just identify about which learning paradigms you feel it. Okay, so after that, let's talk about more detail. Now we focus on the model. So previous few classes, we always focus on what? High-quality data, right? Features, labels. But now let's focus on the model. So what we mean by the model? So normally, a model that we describe an instance of any given ML method. So for example, we might refer a trained neural network as a model. So normally a model will actually include, it's not here, okay, so it includes the parameters and the hyperparameters. How we identify these 2 things? Okay, the parameters is what the model can learn. Okay, if we have different kind of like training data, the parameters will be modified. Okay, the hyperparameter is what we need to set it up before the learning. Okay, so learning is actually we find the best parameter set that suits your training data. So when your training data change, your parameters will be changed. Okay, the hyperparameter is different. The hyperparameter is to identify about the whole structure stuff. For example, for the neural network, how many layers we have, that's the hyperparameter. For each layer, how many neurons we want to set it up, that's the hyperparameter. Okay, so hyperparameter also will be influenced by the training data, but the influence will be very less. Okay, it mostly will be influenced by what? The learning task. Okay, so the whole distribution. Okay, so normally, why we mention this is very important. So we have lots of like open source models currently, right? So all those learning models that you can download it from the, for example, Hugging Face. Okay, so you can learn from their hyperparameters. You can keep their hyperparameters if you are studying the similar problem However, you cannot utilize their parameters because your task, your training data is different, right? Your testing data is different. So normally, what we do is we grab all those models from online. We kept their hyperparameters. However, we utilize our own training data to cover their parameters, and that will turn the model becomes your model. Okay. All right. So we can summarize here. We can think of the parameter as the canop that need to be addressed in a certain way such that the model does what we want. And the hyperparameter are configuration settings that control things like the size of model and the way the learning process works. Okay. So by learning about the parameter and hyperparameter, I also want to talk about the ethical considerations. Because I understand our assessment 1, we do need to consider about ethical considerations, right? So for example, some students choose the Copilot's company is Microsoft, right? Some students choose the Microsoft topic, and their AI product is actually open source. Okay, and some students choose the I don't know what's the company of OpenAI, right? OpenAI they actually provided the ChatGPT, and ChatGPT is not open source. Okay, so what does that mean by open source? This means about the models. If it's open source, you can obtain the models hyperparameter and parameter. Okay. If it's closed, no, you don't know anything. Okay. However, some AI product actually you understand about their hyperparameter. They actually will give you the information. If you search about their original research posts or etc., they will tell you, okay. These AI products, we utilize the LSTM algorithm. This is the structure of LSTM, okay? And perhaps some more specifically, they will give you the full list of the hyperparameter. For example, how many layers they utilize, okay? So how many neurons in each layers, etc. Okay, so that's the case. Part of the model, you will know, okay? But when we consider about the ethical considerations or the privacy concerns, that we normally proceed to when the hyperparameters and parameters are not known, for example, the ChatGPT, if it's supposed to be not known because that's the value of their company. However, if some attacker can actually reconstruct its model, that's what we call reconstruction attack, and that's the privacy threats for this company. However, if someone say that I reconstruct the model of LLM, is that kind of considered about the privacy threat? No, because they all publish the hyperparameter and parameter. Okay, but for the some AI model that published the part, but they didn't release the parameter. Okay, so that will depend. Okay, that will depend. All right, so for the ethical considerations, that's another thing, but ethical considerations, I hope you not focus on the detail about the hyperparameter and parameters, but I hope you focus on more about its answers. I want to hear about the ethical elements between the toxic content to reply. Okay, this kind of thing. All right. So that's the this week's part related to assessment 1. All right. Next is the training and inference. Training of an ML model refers to an iterative process of fitting a model to some training data by optimizing its parameter values. And running the inference on an ML model means to compute or evaluate the model's output for some input data. All right. Another thing that I want to mention about normally in when you utilize AI, okay, Especially, we will have another set of, except for the training set and the testing set, we will have the validation set. Okay, validation set is during the training process. So during the training process, after the model train using based on the training data, they will evaluate based on the validation set. Okay, so validation set is considered as the testing set during the training process. Based on this validation set's accuracy or performance, they will address the training process. They will address their parameters. Okay, so that's the evaluation process within the training sets. That's what we call the validation sets. It normally occurs in AI because there are lots of data. A large amount of data, it will means, we'll talk about that later, will means the overfitting issue. So if that's the case, we will need to introduce the validation sets. All right. Just a hit up here. We'll talk about that later. Before we talk about that later, I want to give a break. Okay, it's already an hour speech, and have a rest. We will be back in 2:05. Okay, see you then. Guys, so just this is just a small chat, okay? I just want to understand, does anyone like really utilize the MLs into one of your projects for practice? Does anyone have this kind of practice? No? Is there like previously joined a kind of like a AI development process? Or even as a data science etc. No? No, this is a small chat. Feel free to go and I'm just so curious, yeah. Yeah.
Last week. So what's the exact difference between tensor matrix?
Sorry, difference between tensor and what?
Array and matrix.
Array and matrix. Yeah, array is just a round bracket.
Yes.
A very simple term. Matrix is 2D. It's 2D. It may be 3D, but
Sometimes we call 3D array, but what is called 3D array as a tensor.
yes,
So
you can consider like array is a unit.
Yes.
Matrix is a multiple unit.
Yeah.
Tensor is kind of a zip of this multiple unit.
Yeah, but what's the difference with the like multi-dimensional array and multi-dimensional tensor?
Multi-dimensional array, they're stored, that they can be the exact same thing. They're stored in different format.
Yeah, I mean, what's the difference in format?
The format?
Yeah.
The tensor format, it's exactly the same. Okay, in nature, they're exactly the same thing.
But in the
Tensor, they zip it for the use of the TensorFlow or Keras, this kind of like a library. They actually is the exact same. However, you cannot visualize the tensor because it's formatted for this library. But in nature, they are exactly the same as the array. Yes,
Okay.
they are the exact same. So when we try to visualize it, we normally will transform it to the array, and then we visualize it.
Yeah.
Yeah, that's the only difference. guys, I just want to, because I'm quite bored here, so I want to find someone to chat. Is anyone like utilize the ChatGPT or Copilot in very interesting way? Does anyone like want to share some story? I can share mine. I previously played a game like the puzzle game. It's kind of like bottle puzzle game. It's like they have like different kinds of bottles, and in each bottle they have different colors. And you just like with the same color you can fill in, and but one bottle can only fill like 4, and they have like always have 2 empty bottles. And there was once a time that I played to like I don't know how many times that and I stuck it. And I said, hey, how about let ChatGPT to help me to figure it out? And I take a picture, I made a screenshot, and I feed it into the ChatGPT, and I say to tell me about how to solve these puzzles. And it was so stupid. The first before, it just because I played to I didn't remember how many. It's like that's the over 500 rounds. So it becomes very complex. They have like 12 bottles, only with 2 empty bottle, and they have more than I can't remember. I think they have more than 7 different colors. The first thing that it becomes stupid is ChatGPT do not recognize the difference between the colors. The second thing is when I describe the rules very carefully, it didn't show it gets the rules. It don't know the limit. It don't know the limits, or it don't know the same color can be put together. Okay, so the understanding, the correctness of their understanding, it depends which rules I put at the beginning. So if I put the limit is at the beginning, then it will follow the limitation rules. If I put the same color, only the same color can put together, it will follow that rules at the beginning. And for the rest of them, it's just rubbish. So the second round that I try to do is to label all the different colors with 1, 2, 3, 4, 5 to 7. And I set the limit with the line. Okay, and I fill in again with the same rules. And I said, okay, because they kind of have like reinforced learning that you can feed in, so you can tell them, okay, your previous one is incorrect, what's the correct one, etc. And then it performs much better. Much better is for the first 3 steps. It's better, and afterwards it do the same thing. And then I just forget. So that's I don't have much patience on this. Does anyone have like very interest use? Yeah. Yes, want to share yours?
So my friend, she has an argument with another friend who takes on WhatsApp, and then she's using ChatGPT to point out if they read red flag in conversation that ChatGPT that she needs. So she put like 50 screenshots into ChatGPT, and then it gave a very nice summaries, and it does point out something. But when look closer, this ChatGPT it doesn't. If you send like a couple message, for example, I send like 3 messages at the same time, ChatGPT didn't know that that's my message. They thought one is my friend, one is mine. Yeah. So
So if you if you send multiple from just your side, it will recognize like the middle of yours with your friends.
yeah, it doesn't recognize that that's all it takes for her. So it does look good. Like if you don't look closer, you should put like 50 screenshot in it. It does look like it gives you a lot of results. But then when you start to put like individually 1, 2 screenshot, Okay, let's look it up. Yeah, it's not very smart. Any interesting use? Which one? Which one?
They have different colors, so like this means they doesn't reach the same height. So because the model is trained, so like because the color different, so which that allow the model to think I'm trying to generate some buildings so that
You try to do more generalization, but at the end you actually do all of this stuff.
yeah.
That's interesting. I did that before actually. I just used, I do remember there was this one time that that's for my experience, and I forgot to utilize the type of the data. And I think it's very important because I don't want it to include the bias. So I utilized these few samples to train. I forgot to address the epoch. And then at the end, it do another way bias. It works very well in those like the minor samples, but for sparsely almost like majority samples. It is well in my cases as well.
So that's what we call interesting bias.
Yeah, no.
Yeah, like a lot of this the air generated.
Yeah, so but at the end I just need to retrain.
Generally, I just go more random, like force the model to go more random and generally, or do you want to use how that you just manage things up?
Yeah, but actually, well, normally we can do some stuff. For example, we just retrain the last layer, but it just because that bias, that minor stuff, that minor image, I think the features at the beginning is quite different. So I want this model to learn the biasing from at the beginning, not this term, because we all know that the first layer is learned about very the large area of his concept, right? So I do want this kind of information to include it in the first layer as well. So that's why I utilize it to retrain the whole stuff. But at the end, it's not working well. Yeah, that's yeah. Sometimes we will call that like training the AI model is sometimes it's just it's just a myth. You know, it depends on the luck. But we somehow summarize some experience by tracing the loss function trend. We talk about how to visualize this kind of thing. Oh, it's the time. All right. I would like to share you. I do have lots of like interesting stuff. Some of my the practice is based on my research because you know my research is AI security and privacy. So there were lots of like especially during these 2 years because we have lots of like generative AI products, right? And they have lots of research papers related to there's some attack that you add this, for example, the surprise mark after the questions, and then you can obtain some toxic content. But if you don't add that, it can be filtered by the current generative AI. It's actually that kind of practice. There was also a paper published, and I will try it. It's quite interesting because normally at the beginnings you will find this okay, it really did work, and afterwards you will find that it's blocked. So except for that, it will be utilized in other very interesting areas. Yes, for example, I will ask it because I'm kind of fan of the Harry Potter. I will actually utilize it to talk about the difference between the
the movie and the book, there was some kind of like a picture in the movie that actually shows someone that's not mentioned in the movie. And I take that kind of like screenshot. I go, okay, tell me who is this person. And sometimes it's good if we talk about based on this character, blah, 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 and actually shows and combined with the description in the book, it actually shows this is that character. And later on, when I go back to that movie to find this character showing other scene, it actually showing very different face and image. So that's another very interesting stuff that I found with the ChatGPT and the Copilot. All right, I could share other kind of practice that I utilize the AI model and other kind of project, but next time. All right. Okay, so let's back to our theoretical part, the boring stuff here. All right. For the purpose of this lecture, we will use a small neural network as the first example of a ML model, and this will be helpful when introducing the fundamental of ML. Okay, so at this point, you don't need to understand how exactly this model works. So that means you can view it as a black box. So briefly talk about the black box and white box. Black box means you just understand this is an ML model. It probably you can understand this is an LSTM model, this is CNN model, but you don't know the rest. But you can utilize it. Okay, that's the black box success. Okay, for example, the ChatGPT is you utilize it within a black box access. Okay, white box access is kind of like Copilot. You can download the Copilot models from their websites, and you can do like model.summary to check out their parameter and the hyperparameter, right? So that's the white box. Okay. Black box, white box, gray box. Gray box is you know part of the information and the rest of the part you don't know. Okay, that's the gray box. Okay, so this is a term we utilize in our technical stuff, but normally when we introduce the AI project to our customers, we will not utilize this stuff. Okay. All right, starting in week 4, we will learn about the most commonly used model for different tasks and input data type. Okay, so here back to the simple digital image classification, right? So the problem we are trying to solve here is to classify the grayscale image of the handwritten digit into 10 categories, which means the label is 0 to 9. And we use the MNIST dataset. This is a very classic machine learning community. Okay. There's one thing, I just thought about that. Okay. There's one thing related to the ethical privacy issues is that sometimes if you do want to risk the ethical stuff, you might utilize the anomaly MNIST dataset. So anomaly MNIST dataset, that's what we call non-IID MNIST dataset. Okay, so this can be extracted from the datasets library. So last week, I don't know whether you guys have already installed the datasets library or not. I do understand that some students are unable to download the datasets library. However, if you successfully download the Torch version, from the Torch version, you can import the datasets library as well. So no worries if you are unable to download the datasets. Okay, so now let's go back. We use the NIST dataset. This is a classic one, and another classic one about the image, the face image. That's the cipher. Okay, if you're interested, you can have a search about that. Okay, so this dataset consists of 16,000 training image and 10,000 testing image. So remember, this 60,000 training image normally include the validation sets, and these validation sets will not be involved in training the parameter, okay? But it will influence in the parameter adjustment. So each image consists of 28 plus 28 pixels. So the weight and length, that is 28, okay? Now, so for example, when I say this is a grayscale image, what's the data type of this image? What's the data type for 28 plus 28 pixels? What's the data type? Okay, the rest of it is the channel. What's the number of channel for this grayscale? Channel? Any idea? Channel for the grayscale image? 2? No. Another guess? Another guess?
255.
5?
255.
255. Close. But no. Yeah. Another guess? Another guess? This is actually related to the quiz questions in the week 1. So although it's very simple, small, but it might relate to your final examinations quizzes part. Okay. So this is what I mentioned here. So grayscale, what we normally put is the one channel. Okay, and this one channel's value is from 0 to 254. So in total, we have 255 like lengths of values, but to represent. But the channel is 1. Okay, channel is 1. All right. So normally, if the channel is 1, the shape will ignore that 1. Okay. So this is why just 28, 28. And the image, the amount is because we have this kind of like image, right? For each image, we will have 28 plus 28 plus 1. All right. So TF, that's TensorFlow, dot keras, dot means call the functions keras from the TensorFlow package. Okay. Within these functions, we will have datasets function. Okay. Well, not only you can extract the datasets function from the torch vision, you can also extract it from the keras. All right. Keras.next.load data. Okay. So this load data will transform the results into these 2 parameters. Okay. So these 2 parameters, one parameter is in size of 2 array. Another parameter is another size of 2 array. Okay, so this one is the training, this one is the testing. Okay, so for these training samples, the shape, as you can see, 16,000, and for each sample, they will have 28 plus 28, and this is the label. So because the label is 1, so we normally ignore it, and same as the testing image. All right, so that's the data set. So after data set, what? We need to build up the models, right? The models is including hyperparameter and parameter. So parameter, you don't need to set up it because it runs basically on your training data we identified previously, but you need to choose your hyperparameter, right? So for this hyperparameter, as I mentioned previously, they will have a few steps. The first step is you copy-paste the hyperparameter from the open source, the models. Okay, the second way, you can set a list of hyperparameter, and then you train based on the training data and compare this set of hyperparameter and identify finally which hyperparameter suits you. Okay. So that's the 2 methods. Okay, this is another kind of like short answer questions maybe occurred in your final examination. All right. So train the model by feeding it the training data. So the training data is include the training image and the training label. So remember the number of training image and the number of training label, they should be the exact same. Okay. So exact same means if it's the 16,000. 16,000, then the label should be 16,000 as well. So after that, the model will learn to associate the image and the label. So in this step, parameters are optimized, okay? So after that, we can set up what's the best hyperparameter, what's the best parameter. That means your model is already here, okay? After your model is already, you can utilize it to do the inference task, okay? So ask the model to produce the prediction for the test image and verify whether the prediction matched the labels or not. Okay, so that's the model. Okay, so that's the workflow. Okay, so look inside to build a model. As we said that how to set up the hyperparameter, there are two ways. One way is copy paste from the previous, another way is to build up by yourself. So how to build up by yourself? The first thing you need to build up the model's structure. As I said, the model structure, number of layers, within the layers, number of neurons, okay? And what else? We think that, for example, this is the type of the layer is dense, okay? Dense is just this is the normal type of the neural network. Okay, so normally we'll put layer dense, and of course we have another type. I don't want to give more detail here because we talk about very detailed in our week 4 or 5. Okay, so I'll just give you a warm up about what's the structure. For example, this is the type of the layer, and this is the number of the neuron. Okay, and this is the activation. So activation is actually the function that you pass your value of these to your next layer. Okay, this is the function. So they have different kind of activation. Regular, softmax. I will talk about that in detail in week. I just forgot about week 4 or week 5. Okay, but we talk about detail here, okay? So except for that, this is what we say. You have already identified its structure. So after its structure, that's what we say, the model. So the model here, as you can, the structure is 2 dense layers. And the layer extract the representation of the data feeding to them. The second layer is the 10-way softmax classification layer. So briefly talk about softmax is normally the final classification layer. No, don't want to give more detail here. Okay, and it returns just the probability score for each digital class. So for each 10 digital class. Okay, we still have like cross entropy here. Cross entropy normally for the binary classification, okay? But this is softmax normally for multiple classification, okay? So this is also kind of like a short answer question for your final examination. I will give you like, for example, this kind of like a structure, and you tell me about, okay, this model is what, okay? And when you see this is softmax, and this is 10, okay? And then you can say this is a 10-way softmax classifier, okay? So that's the model. All right, after this, identify this model, what else you need to consider? Another key hyperparameter is the optimizer. Optimizer is within your compile, okay? So compile, you need to identify your optimizer. It can be the RMS prompt, it can be the other, okay? The loss function, it can be the category, cross entropy. You actually can identify, customize the loss function by yourself, okay, but that's the another way talk about. The matrix, of course, you can identify accuracy, you can talk about recall, etc. Okay, depends on the task. So loss, forgot about loss. Loss is how you measure this performance, okay? How you measure is the function about how you utilize like mapping the true and prediction outputs, okay? And matrix is when you calculate the matrix, the loss function is not just simple like minus, okay? It can be divide. It can be very complex, function. So after complex function, the matrix is not just accuracy. It can be we'll talk about the matrix very detailed later, so I don't want to spend more time here. So matrix just to monitor during the just give a specific value to tell the model whether we need to keep the optimization or not. Okay. All right. So after that, what's the next step? After you build up the model, what's the next step? From the data from the training data to the model we feed in, so there's one more thing very important we need to do is to reshape the original data into the model's requirements input shape. Okay, how could we know the model's expected? So knowing the input shape that an AI model expected is very crucial for you preparing the data correctly. So you will have a few ways to determine, for example, you can check the model's documents or source code. As I said previously, right? The model actually you can utilize the hyperparameter from the open source code, and the hyperparameter actually will identify the type of the input shape. Okay. So most pre-trained model will include it. For example, the TensorFlow, PyTorch, Keras will have clearly defined it an input shape. For example, normally, I want to type it here. Normally, a CNN will have the shape. This is the first shape is the batch size. Okay, the second shape will be the height. The third will be the weight. The fourth will be the channel. Okay, this is the normal type of the CNN. Okay, and this is the one way you can identify what's the expected shape. The second type is you can inspect the model architecture. When you download this model, you say model.summary, and we will give you the visualization of the model. So, for example, just look at the first layer. Okay, when you download it, when you utilize the summarize, you just look at the first layer. It will give you the shape of the input. All right. And what else? What else? If you obtain the formalized training data, you can just, for example, you customize your model, right? You don't need to reshape it. You just, based on the trainings that you collected, to customize your model structure. So that's based on exactly the same. So for example, if I customize it, and then I just utilize the 28 plus 28 as the feature, right? So as this is the same. I would just directly use 28 times 28 as the features, okay? So this is the shape, and all right, so basically 3 steps. All right. After that, after you prepare the data to reshape, you are ready to train the model, and then you call this function, model.fit. Okay. So model.fit is after you identify the model structure, after you prepare the training shape, you pass the training image, label, identify the epoch, batch size here. Okay. To train to your model. And then so you can quickly reach to a high training accuracy, which is larger than 89%. So after the training model, you will find the best suit parameters. So after that, you can run the inference. To run the inference, this is the function you need to do. Okay, .predict. .predict, we think that you just need to give the test image, but do not put the label here. Okay, do not put the label here. Where you need to put the labels? When you need to compare with its prediction results. Okay, so call evaluate function, and then you need to put both test image and labels. Okay, but predict, no. Okay, predict is only get the prediction result, probability. Okay, because previously you utilized softmax, so the prediction is the probability. So as you can see, the prediction 0, that's the least of the highest probability of the outputs in different index. And with the agrimax, that actually means if we have a list of the data, okay, for example, 1, 2, 3 in the index of 0, 1, 2, and it will give the, with the aggregate max, it will automatically give the result is 2, index 2, because it's index 2, okay, index 2. All right, so it gives the result of index 7 because the label is from 0 to 9, right? And index 7 is actually the digital 7. Okay, so that's the meaning of the run inference. So that's all. Now we're going to talk about the generalization and the optimization. So because I actually have some chats with students, some students well know about what's the generalization, what's the optimization, right? So say like here, like optimization is doing well on what you have seen, okay? And the generalization is doing well on what you haven't seen, okay? So that's what we say here. The models never seen, the models have been seen, and models haven't been seen. So the optimization means you're trying to get the lowest possible error of the training data set. So the goal is to minimize the loss function. The loss function is what we say, the classification error, right, on the training data. And the tools, I just briefly talk about here. The tools can be the gradient descent, back propagation, what else? Back propagation, training design, the what else you can do? Oh, learning rate, okay. Learning rate fine-tuning. Okay, so that's the optimization. What's the generalization? Generalization, what I said, is doing well on what you haven't seen. And the tools you can utilize it can be validation set. Okay, validation set is the one way to do the generalization. What else? You can add some noise to the layers. Okay, add some noise to the layers. That's another, what we call differential privacy. Okay, that's another generalization. What else you can do the generalization? Add noise to your training data. For example, the minutes, we can use non-IID. Okay, that's another type of the generalization, kind of. Okay, so normally we need to say if it's over optimization, that means we do very well, over well on seeing the data. Okay, that's what we call the overfitting. What's underfitting? Underfitting is we haven't yet reached to the best performance. Okay, so that's the overfitting. Okay, the optimization is not reached to, is the optimized. That's the underfitting. Okay, so as you can see here, with this, that's what we call underfitting. With this, that's what we call overfitting. So when we map the underfitting, what we normally do? Any idea? Increase the epoch. Because it haven't yet reached to the optimization. What else we can do? Increase the step size. Step size is when we try to learn the optimization, it's actually we increase the step towards the optimization. Okay, so that's another stuff. You don't need to understand what's the step, what's the learning rate. I just want to give you a kind of like concept here, and in our week 4, week 5 or something, you will understand what exactly it means. Okay, so that's underfit. What's the overfit means? Overfit means I overly well performed in this training step. That means I learned not just the normal pattern within this training data, but I also learned some noise within this training data. Okay, so that's the that's the thing. So overfit is, well, I can't say that every model they will have their overfitting problem. Okay, every model. When the model is performed well, they must have the overfitting problem. It's just the overfitting problem is is tolerable or not. With this overfitting problem, there was a very famous attack. It's called the first attack. That actually utilized this overfitting. What this attack occurs, and briefly talk about this theory. Okay, so when we quickly talk about this. We assume that the attacker have the training data set. Okay, so I only have the black box set of this data of this model, and I utilize this model to do the inference on my training data, and I obtain their performance result, right? And then I have another set that maybe not being seen by this model, okay? And then I utilize this model to test on that training set. If it's overfitting, that means it performs bad on its unseen data, or at least comparing to the seen data, it will perform not well on the unseen data. So by comparing their performance, I will know that, okay, this data they utilized in the training model. This data they utilized they haven't utilized in their model's training set. Okay. So it can be an attack. But just think about it another way. It can be auditing, right? So actually this is, if you're very interested in this attack, that's my first work of my PhD, is the audio auditor. So you can utilize this to test whether your model utilizes my data to train your model or not. Okay, and we have the right to be forgotten rights, right? So if I do not want your model to utilize or do not want your service to utilize my data, and when I do the data, I should not find your model have the information about my record. Okay, so that's the overfitting stuff. Of course, we have lots of things to defend it. For example, we have the machine learning. Has anyone heard about machine learning? Okay, so I saw you raise your hand. All right, so that's the particular thing that you can defend the attack from the overfitting issue. So, this is I want to raise this because of this related to the assessment one. When we talk about because you need to consider about ethical consideration, the threats, right? And then to this kind of model, whether they have whether this company have this kind of like allow the users to honor this kind of technique. If they don't have that, they might have some privacy threats. Okay. All right. Example about overfitting and underfitting. So this is an example how you can visualize this. Can visualize the overfitting and underfitting. So with this model fit, you can actually obtain the history. So this history will include lots of the information, including the loss function, including your epoch information, in which epoch, in which iteration. So if you want to understand the whole information about this history, you can delete that and run the model.fit. It will give you this kind of information. Okay, so history is just you create a variable to store those information. Okay, with this history and they have actually a variable called lost. Okay, and they have the variable called validation loss. So this will extract the amount of information and turn it as the list. And we put this list as an X and Y error, and we can obtain into the X and Y axis, and then we can obtain the corresponding loss term, wave, or the validation lost. Okay. So this is the epoch and loss. How we can identify? The training loss is, what does it mean? It means the model's prediction on seeing data. Okay, this is optimization. Training loss shows optimization. Validation loss what? Validation loss shows the performance on unseen data. So that's the generalization loss. Okay. If the optimization is better, much better than the generalization, that it means it's overfitting. Okay. If the optimization is lower than the generalization, that means it underfitting. Okay, so that's how from this kind of like figure, how you can identify in what kind of cases it's overfitting, in what kind of cases it's underfitting. Okay, this is another type of the short answer questions in your final examination. For example, I will give you this kind of like the figure, and I will give you the points, tell me whether it's underfitting or overfitting, and give me the reason why. Okay, so that's type of the short answer question in your final exam. All right, so why we will have this kind of overfitting stuff? Okay, including three things. First, the training data is noisy. Oh, I don't have much information. Have much time. Okay, let's be quick. The first thing is the noisy noise data here, and overfitting means it's not only learn the normal pattern but also learn the noise, right? The second is the training data includes the uncertainty. Okay, because there was some data. Uncertainty means, for example, there was sometimes I just want to drink coffee because of no reason. Like that's kind of like uncertainty, right? That kind of thing. So based on this, you can hardly predict for what reason I want to drink the coffee. Okay, it's hard for you to predict the patterns. And there was a part of time that I give lots of like this kind of uncertainty data. Maybe they can the model is unable to find correct pattern. Why I want to learn, why I want to drink the coffee. Okay, so that's what we say the training data involves uncertainty. And training data includes rare features and suspicious correlations. This will be much, Helen can give you a simple example, so let's go more deep here, okay? So for example, in a real world data set, it's common for some input to be invalid and hence appears outliers, okay? So for example here, the normal way is we just direct here and the performance will be better. However, as you can see, these two stuff, and then we will consider these will be the outliers or unusual cases. By overfitting, that means the model learns the boundary, not just this, it learns the boundary over here. So that is what we say overfitting. Overfitting what it means, when a data, for example, in here, it will classify it as, even though it's a black, it should be the black, for example, here, it should be the black distribution. However, in the overfitting, it will be classified as white. So it will increase the unseen data's performance. Uncertainty in the data. So even the perfect labeled data can be noisy when the problem involves uncertainty. So in classification tasks, some regions of the feature space may be associated with the multiple classes at the same time. Right. So, for example, I get no reason to drink the coffee, and if a coffee shop wants to identify about in what kind of cases the customers will buy a coffee, and if lots of people like me, I just have a thought that I just suddenly want to drink a coffee, and it will hard to let them understand the reason why by analyzing this kind of like data. Okay, and this uncertainty will frequently occurred. Okay, so for example, the model that takes a picture of a banana predicts whether the banana is unripe or ripe. Okay, so there are no objective boundaries between those categories because some kind of the banana, or even though they are look like this grain, it's because of the type, it's actually the red. Okay, so some pictures might be classified as either unripe or ripe by different human labelers. Okay, a model could overfit to such uncertain data by being too confident about the ambiguous region of the feature space. All right, so the real features and suspicious correlations. Suspicious correlations are correlations that appear to be casual, but are in fact just coincidence. Okay, so some examples could be at here. So if you happen to see a black cat before witness an accident on the multiple occasion, you may well become superstitious and assume the black cats are the bad luck. And ML models are no different, right? Because the model trained on the training data set that includes suspicious correlations are highly susceptible to be overfitting. And the real features that are randomly happen to be associated with a label, for example, the black cat and accident. And satisfy the flux in the high-dimensional training data, for example, in a sentiment classification, a certain words may randomly be associated with some positive sentiment most of the time, but it just don't have the real relationship. Maybe just because of this user's habits. Okay, examples. So for example, train the model for two modified versions of the minutes trained data. So first we concatenate over 700 white noise dimensions to the existing over 700 dimension of the data. Half of the data is the random noise. So for comparison, we catalyze the over 700 or 0 dimensions, and half of the data is 0. So comparing the validation accuracy of both models, we can find the validation accuracy of the model trained with the noise channels will end up about 1 percentage point lower, okay, and this despite the data holding the same information in both cases. And the reason for this difference is purely the influence of suspicious correlation. And the third thing is the more noise channels we added, the further accuracy will degrade, okay? So that means the generalization is actually in decrease, okay? Finally, the last part is evaluating the ML model. So this is very important, okay? I would definitely put this into your first short answer question in your final exam, okay? So carefully choose the evaluation metrics. Okay, what else we have? So evaluations will allow us to measure in one number how well the model performed a task. So the different type of metrics for classification task, for regression task, and reinforced task, etc. So metric for single examples or for the set of data. So it may be referred to by the name of the matrix or as scores. Okay, losses are special metrics used specifically for the training neural networks. We will get to these in week 5. But losses normally only considered as metrics during the training phases. Okay, you can't say this is the metrics for a specific model loss. You can't say that. Okay, I got lots of these kind of answers from our previous final examination, but you can't obtain any score because of that. Okay, it's only the metrics during the training phase. After training, when it's the inference step, you cannot consider it as a metrics. Which means, because the inference, the metric for after the inference is actually to reflect the performance of this model, but loss is actually only refer the performance of this step, of this epoch, of this iteration. It cannot represent the performance of this specific model. Okay, so that's why you cannot use loss. So what normally we utilize for the classification task, we utilize the accuracy. So what's the function of accuracy? You need to understand how to calculate this. For example, this is the confusion matrix. Okay, remember how to do the confusion matrix. We normally have predicted class. So predicted task underneath is the number of your model's prediction result. Okay, actual class is your ground truth. Okay, so all these are based on your test data, not training data, test data. Okay, so test data's prediction result and test data's accurate result. Okay, so accuracy is the fraction of correct predictions to total number of samples. What's the correct predictions? When the predicted class is the same as the accurate class. Okay, so the green one are all what we say the correct prediction. Okay, red one will be different. So with different red one, we will have the true positive, we'll have the false positive. Okay, true positive means what? It's correct. It should be, for example, here, it should be A, but it wrongly predicted as B. Okay, false prediction, false positive, it means here, it predicts, it means here, okay, it predicts to false positive, it means it predicts to wrongly, but the prediction is correct. Okay, so that's the false positive. Yeah. False positive. Okay, so this is the difference, but because of the false positive and choose positive, you don't need to understand about their detailed name, but you just need to understand about precision. Okay, so precision recall, F1 score, and balanced accuracy. So this will include all the false positive, choose positive. Okay, normally we say the prediction is choose positive rate, recall is false positive rate. Okay, so precision is a fraction of correct prediction to the total prediction of a specific classes. Okay, so for example, this will be the 6/7. So the over is based on the amount of predicted class. However, the false positive rate is actually considered as here, okay, the amount of 10. So here, yes, it's correct prediction to actual count of a specific class. Okay, so that means this 10 will actually belongs to 6. However, it wrongly corrects as the B and C, and this will be it should be corrected to A, B, C, but it all classified as the A. So this is the precision, and this is the recall. Okay, recall. So sometimes precision is important, sometimes recall is important. So for example, okay, I don't have much time. I would later talk about the for example thing. Okay, F1 score is about the harmonic mean of precision and recall for a specific class. Okay, so basically consider these two. Okay, consider these two as is the times divided by or over class. Okay, these two record. All right, balanced accuracy is the average recall of all classes. Average recall of all classes. That's the balanced accuracy. Okay, so this is how you implement different kind of like the accuracy. But of course, first of all, you need to call from the sklearn import matrix, and from the matrix to call the confusion matrix. Okay, confusion matrix have two input. This is the label, that's the ground truth. Okay, second is the prediction, that's the prediction truth. Prediction result. And accuracy is directly called the accuracy score. Okay, with label and prediction. Precision recall F1 score, you can directly call it from this specific function. Okay, balanced accuracy, they have balanced accuracy scored from the matrix. You just directly call this kind of function. All right. Another thing for regression task is mean absolute error, MAE. That's the mean of the absolute difference between prediction and labels for n samples. So this is the absolute result, absolute difference comparing the prediction results and the ground truth results, and over the overall amount of the samples they have. So that's the mean absolute square. Mean square error, that's for the square difference between the predictions and labels for n samples. Okay, so if I give you this is a classification task, and you choose the MAE and MSE for the matrix, you cannot obtain any scores. Okay, but if I said this is a regression task, you utilize precision and recall, that's not the appropriate choice. Okay. All right, this is the example. Also, you can, from the matrix, this function, you can directly call to mean absolute error and mean square error. Okay, training, validation, and test sets. So the best practice when we evaluating an ML model is so split to the available data from model training. So if they are hyperparameter to be searched, splitting into 3 sets: training, validation, and test. If they have no parameters, splitting 2 sets: training and test. But this is normally for the traditional ML model. But for the AI, okay, when you have very large number of data, no matter whether they have hyperparameters to search, splitting into 3 sets. Okay. So as you can see here, for the training data, mostly it's most data, 60 to 90%. Okay, validation is normally be a small portion of the data, so you can split it from 5 to 20. So this portion is actually suggestions. When you do your assessment too, you can choose the amount of values within this range. Okay, and test is shorter portion of the data, 5 to 20. Okay. So training, the model is most based training on this data, and it will be utilized for the optimization of the parameter. Validation, its model will be evaluated on this data during the training space, okay? Not in the testing space, in the training space. So it can be evaluated multiple times and used to measure the generalization during the training and the feedback signals while we're searching for the good hyperparameters. Test. It's utilized to evaluate it once, that's in your inference phase, okay? It used to measure the generalization of the final model and never previously seen by the model and simulates the production data, okay? So that's the training. So a reason why we don't have is developing a data usually require us to tune its configuration, and that is a hyperparameter. So hyperparameter tuning is a form of learning as well. Across many separated training runs, and we use the hyperparameter performance on the validation set as a feedback signal to choose good hyperparameter. Okay, so however, when we use the test data set to select good hyperparameter, we might suffer from information leakage. So this you can consider it in your assessment 1, okay? But not necessary, okay? Every time we select a hyperparameter value because its performance on the test set, okay? Some information about the test set will link to the model. As I have already given you the example when I talk about overfitting, right? So our model could overfit the test set, performing the artifactually well on it despite never directly being trained on it. And the test set will no longer be reliable, usable to measure the generalizability. Okay. So there were a few things that we can test for the hyperparameter sets. Is sample holdout validation. You can set apart some fraction of the total validation data and hold on some fraction of the remaining data as a validation set and the remaining data as the training set. Okay, so this is the example. Get model is just a defined model to get the hyperparameter set. I will probably talk about these details in our next week's lab. I don't have time now because I have only 2 minutes left. If they have no hyperparameter to be searched, you can create simply chain and set. Okay. So k-fold means to split it, utilize different validation. This one is to increase its generalizability. Okay. And this is the implementation about the k-fold cross validation. Calculation is namely to test about the test of different folds, and you set the average scores as your final result. And this is the hyperparameter search. about example comparison. Okay, so detailed lab I will talk about in our next lab. Okay, so common sense baseline. Has anyone worked this exact problem before? If yes, then it's essential to know what score are achieved for different ML models. That means you have baseline. What score with a randomly initiated model achieve? So for NLIs, if they are 10 equally represented data, then it means it's expected to achieve about 10% validation accuracy for a random classifier. So what is the best score a trivial non-ML model could achieve? If you have boundary classification task where 90% of the sample belong to a class A, that means 10% belongs to class B, then classifier will always predict A achieves 90% in validation accuracy. Okay, so things kept into mind, data representation. So the need to be represented a hand, okay, and interval of time. When predicting the future given the past, it's important to avoid the temporal leak between the training, validation, and test set. Redundancy in your data, it's important to make sure the training they are disjoint. That means they don't have code overlap. All right. It's already 3 o'clock. That's the end of the class. Thank you for attending. See you next week. Maybe I could see you tomorrow. Yeah. See you guys. Bye.